back as far as we can toward the Big Bang, and then come forward in time and watch the process by which galaxies, like our own Milky Way galaxy, have formed. And within galaxies, of course, we will study and continue to study the birth process of stars, how stars in different environments with different chemical compositions can form, and also the death process of stars, by which not only do they come to the end of their evolution, but they replenish the interstellar gas with the chemical elements that go into the formation of subsequent generations of stars. And then this leads to Hubble's work, and very important work we've been doing on how planets are built. We don't see any planets with Hubble Space Telescope around other planets, around other stars, at least not directly imaged. We do see them in transit in a few cases around other stars, as you see in this diagram, and we can probe the chemical composition of the atmospheres of planets around other stars with our Hubble instruments. Then underlying this sort of sweeping panorama of where did we come from, what was the history of the universe taken as a whole, there are the underlying mysteries, the physical processes that really drive and govern the universe that we don't understand. What is dark matter? Where did it come from? And this very mysterious repulsive gravity, dark energy, what in the world is that all about? Hubble played a tremendously important role in the discovery of dark energy, the acceleration of the expansion of the universe, going back to the mid-1990s. And there's still a great deal more Hubble can do before later missions like the Joint Dark Energy mission come along to really focus in greater depth in the particular problem. I like to always say, and it is always true, Mother Nature always has surprises in store for us. And history has shown that ballpark half of Hubble's most important discoveries have been in areas where we didn't even know how to ask the questions when Hubble was first launched. And I think with these cutting-edge tools that we're going to be flying with after servicing Mission 4, it's perfectly reasonable to expect that we're going to uncover new surprises and find that we really didn't know how to ask the right questions in the beginning. Now, let's talk about these two wonderful brand new instruments, and I'll turn it over now to Dr. Bob O'Connell, who is the Science Oversight Committee chairperson for Wide Field Camera 3. Bob?
Thanks, Dave. Let me start with a couple of video clips that show some of the people who've been working for so long, over 10 years, on this camera. And I think we're going to see it being gotten ready to ship to the Cape. And here it is. It's actually two cameras in a single enclosure. And here are some of the people. Of course, you don't know who they are because they're in their bunny suits. And then we're going to see an astronaut rehearsal for installation of the camera. And we hope to be seeing this in real life in another month or so. We do hope it's not going to be quite as wet, however. So the main camera on the Hubble Space Telescope is always the most important camera for astronomers because it operates outside the distorting influence of the Earth's atmosphere. And that's why Hubble has the ability to take these super sharp pictures that we've all become accustomed to. And also, this gives the telescope the possibility of looking in color bands which are blocked from inside the Earth's atmosphere. So in designing this camera, one of our main concerns was to make it panchromatic. That means cover all the color bands that were accessible to it at that altitude, starting in the ultraviolet and going then to the infrared. And we've expanded particularly in those two particular regimes in this telescope, at least in terms of wide field imaging. In both of those bands, this camera is about 10 times more sensitive than any previous Hubble instrument. And that means it reaches the same result for about 1/10 of the time. And by the same token, the camera is about at least 30 times faster than ground-based cameras, and this is because of the influence of the Earth's atmosphere. So this gives us a tremendous advantage or leverage in analyzing a number of different kinds of scientific problems. I'm going to give you a flavor of just a couple of these. I'm going to talk about two instances of trying to understand the star formation history of our universe. Now, star formation is a very important process in astrophysics. We're all in astronomy very interested in that. But human beings have a stake in it as well because the elements that make up our bodies are actually generated inside of stars and then spewed out into the interstellar medium by vast explosions and accumulated in other stars like the sun. And another reason star formation is important for us in a kind of personal way is that planets are a byproduct of star formation. So this is a very interesting process, and of what this camera can do in surveying nearby galaxies, not our own galaxy, but other galaxies nearby us in space, is to kind of slice through the star formation history of these galaxies, kind of dissect that history by doing slices in color. And I have a video here that will show something of what I mean. The first picture you'll see is a kind of an all-band integrated color picture of a galaxy. And then we'll go through it individually in different bands. And this is the ultraviolet band. And you see it looks very different there. And as we go up in color, we go to older stars. The ultraviolet shows the youngest stars. As we go up to toward the red, we see older and older stars. And the character of the galaxy kind of changes. You can see it was rather clumpy in the ultraviolet, but by the time we get to the infrared, it will be very smooth and diffuse and homogeneous. And by doing this kind of dissection, we can tell something about the star formation history of galaxies. And then, of course, you put the whole picture together, as in this image here, and you get a global picture of the star formation history of a galaxy. Now, one of the galaxies we're actually going to be studying in this regard is in the next image. This is a famous galaxy. This has been worked on by Hubble before. It's a product of a collision of two galaxies, and this collision has induced a vast swarm of star cluster formation in the galaxy. And you can see as we move across the surface of this that it's just strewn with these massive star clusters. It's quite a beautiful thing. And we can probe the history of the star formation in this galaxy by using this color technique. Here's a close-up example of one of the kind of clusters that's in this galaxy. This happens to be very nearby us in space. It's not one that's in that other galaxy. But it's a good example of the kind of things that we see. Now, these are all very close by to us, you know, by astronomers' standards. The next problem I want to talk about is at the other end of the universe. And this next photograph you're going to see is an extract from the Hubble Ultra Deep Field, which I think you've all seen before. This is the deepest photograph ever taken by astronomers, and it shows a remarkable variety of different galaxies at an enormous distance from us. The galaxies that you can see there that actually look like galaxies with spiral arms and so forth, those are about 6 billion light years away. That's a long distance. But what we hope to do with this camera is go about twice as far back in space, about 12 billion light years, to look at the things that in that photograph just looked like little tiny blobs. Now, the reason we're interested in those is that they represent some of the first, or we think they represent some of the first galaxies that formed in the history of the universe. And astronomers call this the end of the dark ages. You know, the Big Bang lights up the entire universe. It fills the universe with light, but that decays very quickly. And there's a very long period, lasting for hundreds of millions of years, in which the universe is actually quite dark. There isn't much light in it. But stars have not formed yet because that cooling material that came out of the Big Bang hasn't condensed to the point where actual stars can form. Finally, that's going to happen, and that happens somewhere in the range between 300 million, 500 million, 800 million years after the Big Bang. The first stars start to form in what we call protogalaxies. The first galaxies form, and then the universe begins to evolve to the present. Now, this is a critical transition point. And so far, available telescopes and cameras and so forth haven't really been able to probe this transition very well. But with Wide Field Camera 3, we think we can do that. And the basic problem we face is that these very, very distant galaxies are going to look just like those little blobs in that picture I just showed you. And so the question is, how do you tell which ones are really these distant galaxies at this, you know, at the edge of the universe, the first galaxies to emerge from the Big Bang? And the answer is you use a color technique again, especially with the infrared camera in the Wide Field Camera 3. You take images in different bands, and the galaxies that you're interested in, the things that have these very, very distant, will show up as extremely red, a very strange color, redder than anything we have, you know, around us in everyday life. And that's how you pick these out. And there are a number of programs slated to start in the next year with the first post-servicing cycle of observations, which will be staring at regions of space which are otherwise, you know, devoid of interesting things, and looking for the signature of these very, very distant galaxies. We think this is the first time we'll really be able to probe this era where the galaxies first formed. Now, the final thing